that's where we'll begin. Endocrine function. And it's kind of a segue from what we talked about with GI, because the first group of hormones we're going to talk about have to do with the pancreatic endocrine function. Certainly the endocrine system has very widespread jobs within the body: growth, development, secondary sex characteristics, all our metabolism, and adaptation to the environment. And this was the first class we talked about mechanisms of communication between cells. So we mentioned autocrine and paracrine, which are definitely in play when we were talking about the inflammatory process and the coagulation process and infection. We talked about nerve to nerve or synapse communication. We talked about the nervous system. This is the endocrine system. So one organ releases a hormone that travels in the bloodstream and finds a receptor on a different organ, which tells that organ to do something else. So this is endocrine communication. And endocrine communication either works as a positive feedback system or a negative feedback system. So a positive feedback system means that the hormone becomes amplified because of a stimulus, and the hormone amplification will continue until the stimulus is taken away. So there are other things that work with positive feedback. So the clotting system or the inflammatory process, that process continues to get amplified until bleeding stops or the infection is taken care of, and then those systems get turned off. Hormones, one of the hormones that's created by the posterior pituitary is oxytocin, which is essential for contraction of the uterus during labor and delivery. And the stimulus for oxytocin is when the fetus's head is low enough and putting enough pressure on the cervix that sends a message to the brain, which is interpreted by the hypothalamus, sending a message to the posterior pituitary to release more oxytocin, which causes contraction of the uterus, which then pushes the head against the cervix, and that sends the message to the brain hypothalamus to then again release oxytocin. So that continues to happen until the head pushes through the cervix all the way, and then the baby is delivered. There's no longer the stimulation then, especially after the placenta is delivered. There's no more pressure against the cervix to tell the brain to release more oxytocin because the stimulus is gone. A lot of hormonal systems work in a negative feedback, and the negative feedback is keeping things within, or keeping levels in the body within a certain range. So anything in the body, if this is the level we want it to be, we'll talk about hormones in this way because all of the hormone mechanisms in this section are negative feedback mechanisms. The body is trying to keep things in tight control and maintain a serum level, and if the level gets too high, that tells whatever organ is producing the hormone to stop production, because we no longer need it if we have enough. But then if the level gets too low, that's a stimulus to begin production. Because as long as we're in this range, then we don't have to worry about it. So if it starts to trend up too high, then that's an impetus to stop the production of a hormone. If it starts to get too low, that's the impetus to begin production. So this is another way to do it. We're trying to keep it within balance. So the first hormone production we're going to talk about is the pancreatic's endocrine function. Last class, we talked about the pancreatic's exocrine function, because it does have both. And the exocrine function is the creation and drainage of enzymes that empty into the first part of the small intestine in order to facilitate digestion of carbohydrates, fats, and proteins. The other part of the pancreas is its endocrine function, in which it produces insulin and glucagon mainly. So you can see if this was a cross section of a pancreas, these are what are called acini, sort of like those acini berries. That's the types of pancreatic cells that make the enzymes for digestion. This is the endocrine function part of the pancreas, in which alpha and beta cells create or are in charge of the production of insulin and glucagon. And this is a large negative feedback mechanism in our body. Depending on, what lab you go by, most places will have some variation of you want the glucose to be between 70 milligrams per deciliter and 100 milligrams per deciliter. And that will help the cells, all of the cells, get what they need, because obviously glucose is our main source of energy. When that's inside the cell in the cytoplasm, that's what oxygen uses to produce ATP. So if the blood sugar starts to get higher, then the pancreatic beta cells release insulin, and insulin has a couple of jobs. So what are the jobs? This always seems like okay, we know this, right? But then it's like, oh, I didn't talk about it this way in a while. So what does insulin do? Right. So the overall goal of insulin is to lower the blood sugar. One way it does that is it is the co-transporter. It's what glucose needs in order to be allowed inside the cell. So we allow glucose inside the cell so that the cell can use it for its energy requirements. So because most of the time, especially this being America, when our blood sugar will be much higher based on our intake. And so there'll be more glucose than our cells need. And the insulin has other jobs then. So now we have surplus glucose. What is the first place that can be stored? So fat is the second place. Liver is the first place, correct. So the glucose will facilitate the storage of glucose as glycogen in the liver, so that we have that in between meals. And then if we do have more than the liver, we've reached our storage capability in the liver, then we can facilitate the transfer of glucose into triglycerides and in our fat, whatever's left over. And that these are going to be our reserves for when there might be a time of between meals or starvation. So when the blood sugar starts to go down, that is, there isn't any more impetus for the pancreas to release insulin any longer. Instead, the alpha cells will release glucagon. And glucagon is available in order for us to free up our storage. So the first thing that glucagon does is glycogenolysis, which is to break down those glucagon stores into free glucose and allow that to move into the blood. And then the next thing is to do what's called gluconeogenesis, which is to use our fat as an alternate source of energy, because we can never be deprived of glucose. Our brain can never be deprived of glucose. It has no storage for oxygen or glucose. And so the body will start to break down its fats in order to feed the brain if needed. And that's where we are left with ketones as our byproduct. So insulin is stored in those beta cells where as proinsulin, and it's changed to insulin in the beta cells with a special protein called C-peptide that cuts the insulin. And then there are several types of receptors, that are called glut receptors. And the glut receptors are responsible for the movement of glucose. There's several kinds. So glut on beta cells is the glut-2 receptors, which is what allows glucose to leave those cells and get into the serum. There are glut receptors on our somatic cells, our body cells, in order to help glucose get into those cells with the help of insulin. So this is just everything we talked about. You eat, insulin's released, transported into the cell, go to the liver. We stop the processes that glucagon does. We decrease gluconeogenesis and promote fatty acid and triglyceride synthesis, increase their storage into adipose, increase protein synthesis, and decrease protein breakdown because we're keeping everything built up. And then when the glucose level is low, we release glucagon, which initiates glycogenolysis and will increase transport of amino acids into the liver to convert glucose to form gluconeogenesis. There are other hormones, amylin, which helps slow gastric emptying, and other gut-derived hormones that we talked about last class, like gastrin and CCK and those things that assist. So if somebody has diabetes type 1, they have a failure of the beta cells themselves. Most of the time, that is an autoimmune process, probably a hypersensitivity response that could be initiated by a viral infection. And it is common to occur in juvenile or childhood when that does occur, but it could occur later depending on the person and the other health problems they have. So type 1 is generally considered juvenile onset diabetes, and if there is no beta cells or the beta cells are non-functioning, then there's no insulin, and it doesn't matter how high the blood sugar gets. If there's no insulin, then there's no entry of the sugar into the cells. So that means the body is interpreting, or the body's cells are interpreting, that the glucose level is low. And so we'll switch its work to the alpha cells, which is glucagon, which we're going to start to increase gluconeogenesis. And so it isn't long before somebody with type 1 diabetes with an elevated blood sugar will develop acidosis, because once we switch to this alternative fuel, the byproduct are ketones, which is an acid. And so the blood sugar on someone with type 1 diabetes can be really high sometimes, but usually those people get really, really sick because of their acidosis, which is different than what happens in type 2 diabetes, because it's not an absolute failure of the beta cells. In type 2 diabetes, which had been considered adult onset, although because of the obesity epidemic, children can get type 2 diabetes as well, is your body develops insulin resistance. So how I have always thought about it is that, when someone wears a lot of perfume and they go in a room, and then when you first are in that room with someone with a lot of perfume on it, you're like, whoa, that is really strong. But then as you've been in there for a while, you sort of get nose blind, you get insensitive to that odor anymore because it's always there. And that's kind of similar to what's happening. Usually what happens, what increases insulin resistance, is obesity. We talked when we talked about the cardiovascular unit and a little bit at the end of last unit, that increase in visceral fat will increase the release of several hormones that are pro-clot, pro-hypertension, and pro-insulin resistance. They change adiponectins that are released, which actually increase insulin sensitivity. They decrease adiponectins in the body, and that means they promote insulin. It promotes insulin resistance. So it's going to take more insulin in order to get glucose into the cells. So the pancreas does not release insulin as easily in the presence of glucose, and the body's cells do not take up glucose as easily. So the blood sugar becomes higher. But because there's always insulin, we never switch to the acidosis. So a person with type 2 diabetes can have extremely high blood sugars without being comatose because they don't have the acidosis that people in type 1 do. Instead of diabetic ketoacidosis with type 1 diabetes, they get hyperglycemic, hyperosmotic, non-ketotic crisis. So they have elevated blood sugar and elevated osmolarity without ketosis. So their issue is profound dehydration as opposed to acidosis, which is the problem with our other group. Because, and this is what we learned in the first class, that the concentration or osmolarity of fluid is based on sodium and glucose. Oops. So if the glucose increases, that greatly increases the osmolarity inside the blood vessel. And if the osmolarity in the blood vessel increases, that'll cause cells inside the blood vessel to shift fluid out of the cells, causing cell shrinkage, or it'll decrease filtration and cause fluid from the interstitial space to come into the vessel. And because the patient's kidneys work, that means they're going to urinate more and feel thirsty and eventually become very, very dehydrated. So that's the difference between the crises of elevated blood sugar between type 1 and type 2. It has to do with whether or not you switch into ketosis. Does anybody have any questions before we talk about the thyroid? Okay, so the thyroid is an example of a negative feedback system, and this is one of the hormones of the hypothalamus pituitary axis. That's always a hard word for me to say. So we have our hypothalamus right below the thalamus. Our thalamus, of course, is our relay station, sending messages to the appropriate areas in the brain. So right below the hypothalamus, there's a connection between the hypothalamus and the pituitary gland. The hypothalamus and the pituitary share a portal circulation. That means that the blood that flows between the hypothalamus and the pituitary only goes between those two organs, some of it. Just like when we talked about the liver and the small intestine, there's portal circulation, portal veins that are between the liver and the small intestine on purpose, because we wanted to be able to take advantage fully of the liver's ability to detoxify and metabolize the things that we ingest. In this case, we only want these two to communicate with each other. And so the body has like a separate system, meshwork of venules for them to communicate between each other. And then the pituitary gland will release a hormone that'll affect some sort of organ in the body, causing it to release something. So the thyroid function is one of these particular type of hormone relationships between the hypothalamus, pituitary, and in this case, the thyroid gland. What happens is the brain interprets the need and sends a message called, sends the hormone, oh, I lost my drawing capability. The hypothalamus gets the message from the brain that there's either the normal metabolic needs of the body or there's an increased need related to stress or growth, and thyroid releasing hormone is released and travels through the portal circulation to the pituitary gland that releases thyroid stimulating hormone that travels to the thyroid gland to promote production of thyroid hormone. So in order to produce thyroid hormone, here's our thyroid gland. It's placed below the Adam's apple, or that thyroid cartilage, right anterior to our trachea in the neck there. The thyroid uses, in order to produce thyroid hormone, we need iodine, and so you can have a decrease in thyroid hormone if there's a decrease of iodine in your diet, but that's hard to do in our culture, even if there is food insecurity, because many of our foods have iodine in them on purpose, especially our grains have iodine in them, so it is possible to have iodine depletion, but most of the time in this country we get enough iodine because most salt is iodized. This is how the production of thyroid hormone takes place. So in the thyroid gland, there are specialized cells called, or specialized follicles. These are thyroid follicles, and these are the cells that make up the follicle. And inside is types of protein that are needed to make the thyroid hormone. So inside is like thyroid globulin, essentially, inside that follicle. And we need to bring iodine inside the follicle in order to produce the hormones themselves, which chemically are iodine attached to thyroid globulin. And it's T3 and T4 depending on how much iodine is attached. So in order to allow iodine inside that follicle, there's a receptor on those cells for thyroid stimulating hormone. If thyroid stimulating hormone hits that receptor, then iodine is allowed into the follicle in order to produce the thyroid hormone, which is what this picture is showing you. There's the thyroid follicle. Here's our bloodstream. This is the transporter of iodine and sodium. That won't happen. We won't allow iodine into the follicle unless thyroid stimulating hormone receptor is activated on this follicle, and then we let iodine in so we can put together the hormone, and then the hormone makes its way out into the bloodstream. So we let iodine in because of TSH, we put the thyroid hormone together, and then we let it out into the bloodstream. So T4 and T3 are the actual thyroid hormone. T3 is really the active hormone. T4 is inactive and gets activated in the liver as needed. So it's slowly used. So that's like the storage depot of extra thyroid hormone. And these are the major binding hormones of thyroid within the bloodstream. And we need thyroid hormone for bone and tissue growth, so you obviously would need more of it during times of growth, such as infancy, toddlerhood, school age, and then as you hit your growth spurts. It's part of the stress response because the metabolic needs of the body increase during stress, and it does increase gluconeogenesis and increase energy production and red blood cell production when needed. So some people, it's the furnace, it's the metabolism of our body. It's telling us how fast we need to do these things. So this is a classic negative feedback system. So here's our thyroid hormone that we want to travel through the body in order to assist with catecholamine sensitization to help with protein and bone growth and just our regular maintenance of our tissues. So we want to keep the thyroid hormone, say we're measuring T3, we want to keep that at a certain level within our bloodstream in order to maintain our body's needs. And part of our body's needs is interpreted by the brain in case there's times of increased growth. So thyroid releasing hormone is released from the hypothalamus that tells the pituitary to create thyroid stimulating hormone, which tells the thyroid gland to produce T3 and T4, which circulates in the bloodstream. As the level of thyroid hormone increases, that is a negative feedback to the pituitary gland and the hypothalamus to stop releasing their hormones because we have enough. We no longer need to tell the thyroid to make more hormone if we have enough in the bloodstream. If that level starts to decrease, then that would send a stimulus to the pituitary gland and the hypothalamus to increase production in order for us to maintain this level or to increase it if we need it depending on the needs of the body. So if there is an alteration in thyroid function, if we have too little thyroid production, then we can have a decrease in our metabolic rate and accumulation of kind of mucousy fluid in our connective tissues. And if we have hyperthyroidism, then we have an increase in our metabolic rate and an increase in sympathetic nervous system responsiveness. So either is possible. This would be the normal function. It is possible to have an underactive or too active thyroid gland. So if a person is hypothyroid, it could be that they are hypothyroid. Simply means that there's a decrease in serum thyroid hormone. They have less thyroid hormone than they need. And it could be that everything is functioning normally. You know, the hypothalamus, the pituitary gland would be fine. The thyroid would work appropriately if there was enough iodine to make the thyroid hormone. So inadequate nutritional intake is one reason. If the person had their thyroid removed, well, clearly they couldn't make thyroid hormone anymore. Some medications decrease the ability to make thyroid hormone. In this country, this is the most common reason for hypothyroidism. And that's an autoimmune hypersensitivity reaction to the thyroid gland itself, called Hashimoto's thyroiditis. Something triggers our own T lymphocytes to infiltrate the thyroid gland and cause destruction of the thyroid gland. It can be a virus. It can be sometimes related to different stress responses in the body itself. It's common to develop hypothyroidism after pregnancy, after a time of great stress. If someone has hypothyroidism, then their metabolic rate decreases. So we would expect signs that the body has slowed down. So there's mental and physical sluggishness, increased fatigue, because it's in charge of sensitizing or helping the sympathetic nervous system work, we could have decreased heart rate and decreased blood pressure. It's going to slow our GI tract down, so we may not be as hungry, might be constipated. It'll decrease our respiratory rate. People will be more cold. They could gain weight. There might be changes to their hair and nails, making them more coarse and dry. Myxedema is that accumulation of these mucopolysaccharides, which there's like jelly-like substances in the connective tissue, which is common with people who have severe hypothyroidism. That doesn't just occur. You have to have, in order to get this waxy sort of appearance, or like this woman has before her thyroid is corrected, the thyroid has to be way off. The highest range of thyroid dysfunction in terms of hypothyroidism is something called a myxedema coma, meaning this is the end stage of hypothyroidism. The patient is in cardiovascular collapse with severe metabolic derangement. It is possible to be born with congenital hypothyroidism, which could lead to physical and mental disability later in life, which is referred to as cretinism. So if somebody was hypothyroid because they had a non-functioning thyroid gland, because either they had congenital abnormality, or for most adults who develop hypothyroidism later in life, they had a lymphocytic infiltration of their thyroid gland, then we would expect that their thyroid releasing hormone level, what the hypothalamus releases, would be elevated, and the thyroid stimulating hormone level, what the pituitary gland release, would be elevated, because our body is trying to stimulate our thyroid gland to produce hormones. And if it is unable to do so, the pituitary gland and the hypothalamus never get that negative feedback to tell them to turn off. That doesn't happen if we don't create those hormones. So you may notice, or if you are hypothyroid, you might know this already, that sometimes people measure thyroid function indirectly by measuring the TSH level. Because if someone's thyroid gland is not functioning, we would expect their thyroid stimulating hormone level to be high, because that message is being sent to the thyroid to produce thyroid hormone. Is just not able to for whatever reason. So you could test thyroid function by actually testing the free and bound thyroid levels, or you can indirectly test thyroid function by doing the thyroid stimulating hormone. It is unusual for the problem to be at these levels. People who are hypothyroid because of a problem in the pituitary gland, that can happen if someone has a condition called hypopituitarism, and that would mean they would have multiple hormone dysfunctions, because the pituitary gland is responsible for many hormones. And if that was the case, their thyroid level would be low, and so would their TSH level be low, because their pituitary gland wasn't functioning, but their thyroid releasing hormone level would be elevated. It is even more uncommon, but possible, for the reason the thyroid gland isn't functioning is because it's actually not receiving messages from the hypothalamus, and that would be related to more of a brain trauma in general. And again, the patient would have other symptoms besides thyroid dysfunction. Then we'll talk about hyperthyroidism before we take our break. Does everybody understand hypothyroidism so far? Okay. So it is possible to develop hyperthyroidism. You can develop a multinodular or a thyroid nodule that overproduces thyroid hormone, or you could have diffuse overproduction or Graves' disease. And so in that instance, the thyroid gland itself becomes enlarged versus nodular. But there is an overproduction of thyroid hormone itself. And so the manifestations of hyperthyroidism are obviously the opposite of the manifestations of hypothyroidism. Instead, our metabolic rate is increased. So we're more hot with more sweating, our hair is thin, we're losing weight, our respiratory rate increases, our heart rate increases, our blood pressure can be higher, we might have diarrhea instead, we're awake, irritable instead of depressed, and instead of a myxedema coma, our worst manifestation would be a thyroid storm. Usually with Graves' disease, this state of hyperthyroidism, the thyroid hormone is large in general, and commonly what's called ophthalmopathy or exophthalmos is the protruding eyes, as there will be an immune inflammation of leukocytes that are sort of pushing the eyes forward. What happens in this situation is that the patient is creating thyroid stimulating immunoglobulin. So their own immune system has made an immunoglobulin that is similar to TSH. So their thyroid gland is being overstimulated. So we have that follicle that we talked about before that has a receptor on it that's supposed to be for TSH, that when TSH comes on the receptor, then we pull iodine into the follicle and then we can get the hormone to come out. People who have Graves' disease have a thyroid stimulating immunoglobulin that acts just like TSH to produce more thyroid gland. So a thyroid gland that is overstimulated, what happens to cells if they're overstimulated? Enlarge, right. This is a hypertrophy. So the same, again, from the first class, we develop hypertrophy and hyperplasia. So the person with Graves' disease has a diffuse goiter, just a diffusely enlarged gland. And so, as opposed to a nodule, sometimes people will develop nodules, which can be precancerous or cancerous, that oversecrete thyroid hormone, and that's a little bit different than Graves' disease. The thyroid storm, instead of us having a circulatory collapse like we did with myxedema coma, instead now we have tachycardia, angina, high fever, restlessness, and the possibility of death as a higher mortality rate than the myxedema coma. So that's thyroid. So if the person had Graves' disease, let me just be sure we have that down. The person has Graves' disease, so they have, this is an autoimmune disease that has increased production of thyroid hormone because of that immunoglobulin. So we have that hypertrophied thyroid gland and we have extra thyroid hormone. I would expect that the hormones that normally, thyroid releasing hormone and thyroid stimulating hormone, those are the normal stimulants for production of thyroid hormone. Since this thyroid is high, these would be very low because of negative feedback. There's no reason for these to be released because we have way more thyroid hormone than we need. So I would expect TSH and TRH to be low if I were to check those. So it's 7:50 right now. Before we talk about hormones of the adrenal gland, we will take a break until 8 o'clock. So that's when we'll be back. So I'm just going to